All right, today we're going to tackle the world of numbers. We're going to build a super simple but really powerful guide that'll make this whole thing crystal clear. You ready? Okay, let's jump right in.
So let's kick things off with a little puzzle. What in the world do these three numbers have in common? You've got pi, that endless kind of mysterious number. Then there's -5, super straightforward. And finally, 1/2, just a simple fraction. I mean, they look like they're from totally different universes. But believe it or not, they share a fundamental connection. So, what do you think?
The answer? They're all real numbers. Seriously, that's it. That's the big secret. If you can imagine a number and find a spot for it on that infinite line from math class, then boom, it's a real number. Think of that number line as our trusty map for this whole journey. So, how are all these numbers organized? Well, you can think of it like a family tree. Or, you know what's even better? Like a set of those Russian nesting dolls, where each group of numbers fits perfectly inside a bigger one. Let's start unparking these dolls, one by one. Okay, let's watch this family grow. We start with the absolute basics, the natural numbers. The ones you learn to count with. Then we add just one new member, 0. And suddenly we have the whole numbers. Next, we invite all the negatives to the party, which gives us the integers. And finally, we throw in every possible fraction, and that creates the huge extended family of rational numbers. You see how each new group just swallows up the one before it? Okay, so here's a great little cheat sheet for us with all the official symbols. But check out that last row, irrational numbers. These guys are the rebels, the outliers of the number world. They are totally part of the real number family, but they just don't play by the same rules as everyone else. They're a whole separate branch of the family tree. And honestly, this is where things get really interesting. And that brings us right to the Great Divide. This is it. This is the absolute key to understanding the whole real number system, telling the difference between rational and irrational numbers. Once you get this down, I promise, everything else just clicks into place. So here's the deal, and it's actually pretty simple. Rational numbers are neat. You can write them as a nice, clean fraction. And if you look at their decimal form, it'll either stop or it'll repeat in a predictable pattern. Irrational numbers, though, they're wild. You can't write them as a simple fraction, and their decimals just go on forever and ever with no repeating pattern at all. Let's see what that actually looks like. Okay, let's look at 0.25. The decimal just ends. It terminates. That's a classic neat number, which tells us it's rational. And yeah, of course, it's just the fraction 1/4. Now, how about this one? 0.272727 and on and on. See that repeating 27? That beautiful, predictable pattern makes it another neat number. So, yep, it's also rational. And here's where it gets wild. At first, you might think, oh, there's a pattern here. But look really closely. The number of zeros between the ones keeps changing. It goes from 1 0 to 2 to 3. There's no single block of numbers that repeats over and over. This is a wild decimal. It's never going to end, and it's never going to repeat, which makes it irrational. All right, so now that we've got the lay of the land, let's talk about some power tools that'll help us work with all these numbers. We're talking about exponents and surds, and they're going to make things so much easier. Exponents are basically a superpower for numbers, a total shortcut. I mean, instead of writing out 2 times 2 times 2, who's got time for that? You can just write 2 to the power of 3. It's clean, it's simple, it's awesome. And of course, with great power comes a few rules. These laws let you handle exponents like a pro. We're not going to dive deep into all of them, but I really want you to look at that last one, the zero power rule. Anything, literally anything, to the power of 0 is 1. That's a bit of a mind bender, right? But trust me, it's a super important rule you just gotta remember. All right, next tool in our toolkit, surds. The name sounds kind of weird, I know, but the idea is actually super simple. A surd is just an irrational root, and I've got a little trick to help you spot them every time. We're gonna call it the neatness test. Here's how the test works. Let's take the square root of 9. Does it simplify down to a nice, neat number? You bet it does. It's 3. A perfectly rational integer. So that is not a surd. Okay, now what about the square root of 3? Does that simplify neatly? No way. You get that long, wild decimal we were talking about. And since it's not neat, it is a surd. See? Simple as that. So we've got our classifications, we've got our power tools, but what's the point? Why does any of this actually matter? Well, let's put it all together and see these ideas in action. This is where the rubber meets the road. Let's tackle these 3 together.
First step, the square root of 49. Does it pass the neatness test? Yep, it simplifies perfectly to 7. That's a neat integer, so it's rational. Easy. Next, the square root of 7. That is not going to simplify neatly. It's one of those wild decimals, so it's irrational. And finally, 0.375. Well, the decimal stops, it terminates. That makes it rational. See how those rules just start to click? Before we wrap this up, let's go over a few common mistakes people make, just so you can avoid them. First, don't assume every decimal is irrational. Remember, if it repeats, it's rational. Second, please don't forget the zero power rule. Anything to the power of 0 equals 1. And finally, if a root simplifies to a nice whole number, like the square root of 16, it is not a surd. It failed the neatness test. And there you have it. These rules, they aren't just for a math test. They are the hidden logic, the secret code that powers everything from the bridges you drive across to the algorithms in your phone. They're literally the building blocks of our modern world. So the real question is, now that you get it, what are you going to build?
You know, when you look at numbers, do you ever get the feeling there's something deeper going on, like a hidden set of rules, a secret code that connects them all? Well, guess what? There is. And today, we're going to start cracking that code together.
To get started, I want you to just try on this one simple idea. Let's just imagine for a second that every number you can think of, 10, 53, a billion, is really just a structure built out of Legos. So you've got these small, simple structures, like the number 6. And then you have these massive, sprawling, complex ones, like, 1,937. But what if I told you that all of them, no matter how big or small, are all built from the exact same set of basic, unbreakable pieces?
Well, those pieces, they're called prime numbers. These are the fundamental Lego blocks of our number universe. You just can't break them down any further into smaller whole number parts. A 2, a 3, a 5, a 7, they are what they are. They're like the atoms of math, the building blocks for literally everything else.
Okay, so if primes are the Lego blocks, how do we actually build with them? Well, this brings us to a huge idea, something I like to call the unique number recipe. Now, the official name is the fundamental theorem of arithmetic, and believe me, it is one of the most important concepts in all of mathematics.
And the idea itself is it's beautiful. It's so simple. Every whole number, bigger than 1, has its own unique recipe, and the ingredients are always just prime numbers. That's it. Take the number 12. Its recipe is always 2 2s and a 3. Always. You can't snake a 5 in there, you can't build it with 7s. Those ingredients are set in stone.
Now, of course, in math, we have a more formal way of saying this. It's written out in a statement that looks a little intimidating, right? But don't let all the symbols throw you off. All this is really saying is exactly what we just talked about. Any number n is just a product of a unique set of primes, p1, p2, and so on, where each prime is used a certain amount of times. It's just the official, written-down recipe card.
So how do you find this unique recipe for any given number? Well, we can just break it down. Let's take 180. We start by dividing by the smallest prime we can, which is 2. We do that, we get 90. Can we do it again? Yep, we get 45. Now we can't use 2 anymore, so we move up to the next prime, 3. And we just keep this process going until all we're left with is a prime number. And there you have it. The unique recipe for 180 is 2 2s, 2 3s, and 1 5.
All right, so we know how to build numbers from their prime ingredients. Now let's talk about the rules of the build. This is where a concept called divisibility comes in. And really, it's just about understanding how these different Lego structures can fit together.
Let's just stick with our Lego metaphor, because it works so well. Saying that one number A divides another number B is really just asking a simple question. Can I build structure B perfectly with no pieces left over using only blocks of size A? So, for instance, we can say 3 divides 12 because, hey, you can build a 12 using exactly 4 3 blocks. Simple as that.
The way mathematicians write this down is with a little vertical line, like this, A/B. It just means that B is equal to A multiplied by some other whole number, which we call K. It's the exact same idea we just talked about, just in math speak.
And this simple definition leads to some really powerful and honestly common sense rules. I mean, think about it in Lego terms. If you can build one tower using only 4 stud blocks, and you can build a second tower using only 4 stud blocks, it just makes sense that if you stick them together, the new giant tower is still made entirely of 4 stud blocks, right? That's all these properties are saying. They're the basic logic that holds all of this together. Okay, so knowing the rules is one thing, but the real magic, the real art in all of this is explaining why the rules work. And that's all a proof is. It's not scary, it's just a crystal clear step-by-step explanation that proves something is true. Not just sometimes, but always.
Let's prove something we all feel in our gut is true. Add two even numbers, you get an even number. But how do we prove it? Well, first we have to define what an even number is. It's just 2 times something. So we'll call our two numbers 2m and 2n. Then we add them up. Now here comes the key move. See how both parts have a 2? We can pull that 2 out front. We factor it. And just like that, we've shown the sum is 2 times some other number. And if it's 2 times a number, well, by definition, it has to be even. And we're done. That's a proof.
All right, let's try one more. What do you think? If you take any odd number you can imagine and you square it, is the result always going to be odd? You can try a few. 3 squared is 9. That's odd. 5 squared is 25. Also odd. Seems like it works, but how can we be absolutely sure it works for every single odd number that exists?
We're going to follow the exact same pattern. First, what is an odd number? Well, it's just an even number, 2k, with 1 added to it. So, 2k plus 1. Now we square that whole thing. When we multiply it out, we get 4k squared plus 4k plus 1. And the real secret is in that next step. We can pull a 2 out of those first two parts, and what's left behind tells us everything.
Look at that. This is the aha moment. We've got 2 times something. It doesn't even matter what's in the parentheses, plus 1. And what's our definition of an odd number? It's an even number plus 1. The proof is right there in that little leftover plus 1. It's just so elegant, isn't it?
And this brings up a really, really important point, a common trap. Testing an idea with a few examples is a fantastic way to see if you're on the right track, but it is not a proof. Saying, well, 3 plus 5 is 8 only proves it works that one time. A real proof, a solid proof, uses variables like m and n to show that the logic works for all possible numbers every single time.
So at this point, you might be thinking, okay, this is pretty cool, but is any of this actually useful? Oh, you have no idea. Let's see how these seemingly abstract ideas about numbers are the foundation for some incredibly powerful, real-world technologies.
I mean, just think about this. The security for pretty much everything you do online, your emails, your banking, all of it, relies on that unique recipe idea we started with. It turns out it's easy for a computer to multiply 2 massive prime numbers together, but it's almost impossible for it to take the result and figure out the original recipe. That difficulty is literally what keeps your information safe. And it goes way beyond that. This stuff is at the heart of computer science, it's a cornerstone of competitive math, and honestly, it's just one of the best ways to train your brain to think logically.
So, you know what? It's your turn. Let's see you be the mathematician. Here's a challenge, a classic problem you might see in a math competition. Can you prove that if you take any 3 consecutive integers, like 4, 5, and 6, and add them up, the sum will always be divisible by 3? I'll even give you a hint. Try representing them with a variable. Go ahead, pause and give it a shot. And I'll leave you with one last question to ponder as you go. Think about our unbreakable Lego blocks, our prime numbers. If a prime number can perfectly divide the product of 2 other numbers, does that mean the prime had to be an ingredient in one of those original 2 numbers? Think about their unique Lego recipes. The answer to that question is another one of the great pillars of number theory. And now you have the tools to start figuring it out for yourself.